Hello and welcome to the use of GenomeStudio for automated polyploid clustering. The purpose of this short demonstration is to introduce you to the features of GenomeStudio's polyploid clustering module, which is being launched by Illumina in conjunction with the GenomeStudio genotyping module. What I'm showing here is the start menu for the computer that I'm working on. The GenomeStudio installed here includes two modules. The module labeled genotyping refers to the standard diploid clustering and genotype calling software. This would be appropriate to use when analyzing data on a diploid genome like human, cow, or chicken. It would also be useful for doing a manual analysis and genotype designation for polyploid species for up to 9 clusters. There's no plan on changing the standard Illumina Genotyping Studio genotyping module. The new module and the subject of this demo is the automated polyploid clustering module, which is a component of the genotyping software. To open a project within the new polyploid clustering module, you'll need to have already created a project within the genotyping module. So you will need to have already installed the genotyping module with a key, and then installed the GenomeStudio polyploid clustering module after installing the GenomeStudio genotyping module. So to open a project, you'll click on the module name in the lower left from within the GenomeStudio portal. What this is showing is the GenomeStudio portal, which users of GenomeStudio are quite familiar. GenomeStudio portal allows you to keep updated on special alerts for GenomeStudio, as well as get links for updates to the software. This is where you can find the link to the update for the polyploid clustering module installation. Once you click on this polyploid clustering link, you'll get an open browse dialog, and you'll be able to browse to a genotyping software program that's already been saved, a BSC file, and you can open that within the polyploid clustering module. If you instead use the File Open Project, the project will by default be open not within the polyploid clustering module, but instead within the standard diploid genotyping module. Now, the PC module is paired and is always installed side by side with the genotyping module, as we mentioned before. Once you open a project, you'll recognize the familiar aspects of a genotyping project. This includes the full data table, the SNP table, the samples table, and the SNP graph, which are all visible by default. It's worth mentioning that in the samples table, I've made visible some legacy columns from the genotyping module and their corresponding columns for the PC module. For example, call rate is a column that reflects the call rate from the project in the genotyping module. This is static once in the polyploid clustering module and does not get updated, so it's shown in red to reflect this. In the PC module, you want to pay attention to the poly call rate, which corresponds to the ratio of SNPs of the total for which that sample has cluster assignment. Poly 50% is a column that is used instead of the P50GC that some folks may be familiar with from the genotyping module. And poly 10% is the column that gets updated instead of the P10GC. Poly 50% and poly 10% are the 50th and 10th percentile, respectively, PolyScores for all SNPs within the samples table, or for all samples within the SNPs table. PolyScore can be thought of as a PC module proxy for GenCall score. So it ranges between 0 and 1 and gives a relative confidence that a sample has been accurately assigned to a cluster. We'll talk more about this later. So this demo is intended for advanced users who are familiar with the use of GenomeStudio's genotyping module. And if you're not familiar with it, we recommend that you enroll in the GenomeStudio Basics course available in the Illumina's Learning Management System. So please contact customer service for assistance in accessing the LMS, or the Learning Management System. So I'll switch over to an actual live version of the software to demonstrate that in the Polyploid clustering module, there are 4 ways to access the clustering submenu for automated clustering. And it's important that no samples be selected when clustering for multiple SNPs, or this will confuse the algorithm. So if you're having any trouble getting it to respond to clustering, just deselect samples. So if a sample is selected like this, you just click within the SNP graph and that'll deselect that sample and you'll be fine. So methods to get at the clustering submenu are within the analysis menu, cluster selected SNPs as, and you'll get this clustering submenu. You can also right-click within the full data table to get this submenu, or within the SNP table to get that submenu. You can right-click within the SNP graph, but that will just cluster this current SNP. It will not cluster multiple SNPs within the SNP graph. And when you're in the SNP graph, you can select samples and have several other options within that submenu that you can play with and spend time with, especially if you're interested in doing manual editing. There are also several keyboard shortcuts that allow you to access the menu options more quickly once you're familiar with them. So I'm going to go back to the PowerPoint and show you more information about the clustering submenu. So here's the clustering submenu, and here's a close-up of that menu. The clustering submenu has features that leverage either DBScan or the optics algorithm. These are density clustering algorithms that have been published through the Institute of Computer Science at the University of Munich. DBScan is a density-based algorithm for discovering clusters in large spatial databases with noise. And optics was developed later as an algorithm subtype to DBScan. Optics is a little more robust to input parameters, so use of this would be beneficial for minimizing manual editing of clusters while maximizing call rates. Optics does come at a cost, though, so you'll notice that it takes longer to compute for it to run on large projects. So back to the clustering submenu. If you choose one of the first 2 settings in the clustering submenu shown here, these are D and O lines, the PC module will identify clusters based upon the parameters of the relevant algorithm and the population of points present at each locus, with no a priori assumption of how many clusters should be present at each locus. That's the nature of these algorithms, these density-based algorithms. Within this same submenu, you'll see that you can also cluster for a specific number of expected clusters. So in this case, 1 through 7. Currently, we have set the maximum number of clusters as 7, but this is editable, so you could have 9 or 20 showing here. So there's 7 different choices right now for the number of clusters to expect right now, and it can be changed to any maximum number. The final 2 options in the submenu will make more sense once we've gone over the clustering options dialog, where you can set parameters for DBScan and optics. So this optics decremented and optics incremented we'll talk about in a minute. To access the clustering options dialog, go to the Tool menu within the main GenomeStudio workspace. And once that's open, you can see that there are several parameters that can be adjusted to change the sensitivity of each algorithm to identify clusters. The first parameter is minimum number of points in a cluster. This is the min points parameter that's talked about in the publications from the University of Munich. This is the minimum number of points that GenomeStudio needs to find within a given area to define a cluster. When I say given area, that given area is the next parameter, which is called cluster distance. And we'll talk about that in a minute. Users should be familiar with the population of interest to set the minimum number of points in a cluster based upon their thinnest cluster. So this might be an outlier or an outgroup of samples you expect to cluster together. This minimum number will likely be higher with higher sample numbers in the data set. It's probably a good rule of thumb to set this at 1 to 5% of the number of performing samples among your loci. I think it's a good place to start. So back to cluster distance. Cluster distance is also a user-defined parameter for both DBScan and optics, and you can set them separately here. Cluster distance is the maximum distance in units within the SNP graph that is tolerable before a point is considered to be outside of the cluster. As such, this is the given area within which we expect to see the minimum number of points in a cluster, which we've designated previously. If points are separated by more than the cluster distance, then they will be left outside of a cluster or be part of another cluster. DBScan and optics both have a cluster distance parameter, but optics has an extra parameter, which is a convenience parameter. You can manually change your cluster distance and then recluster, or you can increment the cluster distance and recluster simultaneously by using bracket keys or the H or L in the keyboard. The bracket keys will increment and decrement the cluster distance so that you can quickly see the effect of different cluster distances. So the amount by which the cluster distance is incremented or decremented is determined by the value set in the options dialog box. So that's right here, cluster distance increment. And then just to show you quickly how that looks in the clustering submenu, it's right here, optics decremented, L or a left bracket, optics incremented, a H or a right bracket. The next option in the options dialog box is the maximum number of clusters in the SNP table. The setting of this parameter determines how many choices will be seen in the clustering submenu and how many subcolumns you will see in the SNP table, displaying the cluster identity for each sample. Also in the options dialog box is this confidence score limit. So this is right here. The confidence score is also called a PolyScore, and it's calculated for every sample at every SNP and has a possible value between 0 and 1. And the values closer to 1 suggest a higher relative confidence in the cluster assignment. It reflects how reliably the sample belongs to that cluster to which it's been assigned. So the closer the sample is to the centroid of the cluster, the closer the score will be to 1. It's important to understand that this is not a p-value and it's not a probability, but a relative population-based confidence score. The option to highlight samples below a threshold allows you to view samples within a given SNP graph that fall below a threshold that you've set. Okay, back to the clustering submenu. There are several keyboard shortcuts that can be used to make the process faster for clustering. For example, you can type an O to launch the optics algorithm or a D to launch the DBScan algorithm. And when those are launched, they'll be launched relative to those options that you've already set in the clustering options dialog. Keyboard shortcut cuts are all listed within this submenu here. And just to go over a few definitions and to conclude the presentation, for a locus, and these are useful values to use, for a locus, poly 50% is the median PolyScore, and we mentioned this earlier, but it's the median PolyScore if you sorted all the PolyScores, and these are the relative confidence scores, for all samples at a single locus. For a sample, the poly 50% is the median PolyScore if you sorted all PolyScores for all SNPs for that sample. And then in poly 10%, this is the 10th percentile PolyScore if you sorted all PolyScores for all samples at a locus. And for a sample, the poly 10% is the 10th percentile PolyScore if you sorted all PolyScores for all SNPs for a sample. Now, again, the benefits of the Polyploid clustering algorithm is there's no assumptions about cluster shape. It accommodates noise in the data. It's automated, very little user-defined information, minimum points being the most important. And the minimum points guideline is 1 to 5% of performing samples of the locus. This should be 5%. And then just a little mention about the difference between DBScan and optics. And these publications are available as well. DBScan was an algorithm that was developed first. Optics is a sub-algorithm of the DBScan algorithm. DBScan allows for more manual adjustment of clusters, and it's a little more conservative, so things will fail and be left out of clusters more easily within DBScan generally, using the same parameters. Optics is a little more robust to incorrectly set minimum points, but it also takes more compute time. So, and that concludes the parameters within the new Polyploid clustering module, and now let's look at some real data.
Hello, I'm going to dive into to show you how exactly to use the new Polyploid clustering module to analyze the hexaploid weight data. So we just heard the very good overview how the PC module works, and so in this presentation, I'm just going to show you.
To unmute your line, press *6 or #6.
So here is the software. I just open it up, and then I'm going to open up a project. So this project has 450 samples. For 450 weight hexaploid weight accessions, and has been genotyped with weight 9,000 SNP array. So from this 9,000 SNP array, we have 8,600 SNPs that has the assay results. So on my main windows, I like to show 4 different panels. So underneath this, I usually like to see the original scores. Okay, so but that shouldn't affect anything for the clustering. But anyway, so let's start with the clustering. And so I have been playing with data sets for a while, and so I actually found out that 0.6 would work a little bit better. So I'm going to just go ahead and change this to 0.06, and so let's start clustering the SNPs. So I'm going to move to the SNP table. And I'm going to just pick the first, okay, let's say a few thousand. And I'm going to do the optics. All right, so because wheat is allo hexaploid polyploid, and with 3 genomes are very similar to each other. because of this copy number can affect some of the cluster position. So often one of the cluster has been shifted. And because wheat is a self-pollinated crop, so in most cases I would expect to see only 2 clusters. So what I do next to check how the clustering is doing is normally I like to sort the number of clusters. Okay, so I'm going to pass this poly 50%, all the parameters and everything, just assuming everything works well. And I'm just going to show you exactly how I do the following cluster editing. So what I do usually is to sort the number of clusters by the ascending order, by the descending order. Okay, so you see there's some SNPs actually showing more than was showing 10 clusters. So anything that showing giving me 3 or more than 3 clusters, I would like to see exactly what's going on. So for instance, like in this case, this is a pretty complicated pattern. So in most cases, I probably would like to ignore them anyway. Okay, and so let's take a look at the ones that are showing 4 clusters. And so in this case, I think those are probably could belong to the same cluster. So if I say I think those samples should be all belong to the same cluster, what I do is I can just highlight those samples. Okay, before I do that, and I think I should show legend. So in the legend, it shows you the number of clusters, and within each cluster, how many samples are in that cluster. So I can just highlight those samples, and then I say, okay, I want to assign those all in the C1 cluster. And here you see all the samples are in the C1 cluster. So that's how you do the editing. And so for instance, like this, I probably could just say it could belong to C3. All right, and so that's how we do the editing. So so under that, the parameter I was using, I think they are pretty good for separating clusters that are very close to each other, separated by probably 0.2 theta value, 0.2 or 0.3 theta values. Okay, so we can take a look, an example. For instance, like these 2 clusters are pretty close to each other, okay, within theta value of 0.2, so that's pretty good. But in some cases that some of the clusters are, if the 2 clusters are way too close to each other, and then we need to modify the parameters a little bit. So in other words, that not only I need to check the SNPs that give me 3 or more than 3 clusters, I also want to check the SNPs that give me only 1 cluster, because there could be 2 possibilities that for this 1 cluster. One is the SNP just being non-polymorphic, and the other possibility is that the cluster just being too close to each other, and the parameters are not optimal. Okay, so let's take a look at those with just 1 cluster. And so these are all now polymorphic. So in this case, that's obviously there are probably 2 clusters over here. So what I do is usually I go back to the clustering options, and then I lower this number down to 0.03, and usually I find this pretty good. So let's have a look, and then we'll go ahead and do the optics clustering. Okay, here now I got to these 3 clusters, and then I think those 2 probably should belong to the same cluster. So I just say I want this assigned to the first cluster. And here we go. We have 2 clusters. Okay, so you can find another example like this, and then I'm just going to go ahead and use the same parameter. And so I'm going to hit the letter O on my keyboard. Again, here we see very nice 2 cluster, and this is probably, you can see, so these samples are probably could belong to the same cluster. All right. So this new PC module actually is quite helpful comparing with the genotyping module, because the genotyping module we have to actually go in and then assign the samples, assign the cluster that was actually shifted. And this new PC module, you don't have to do much, and the editing is actually pretty easy, and you can just there's a lot of shortcuts. You can just hit on the keyboard and do the clustering. So this is in a nutshell how I do the clustering and then also editing the clusters. So the next thing is that once I've done editing all the clusters, and I'm satisfied with all the with the clusters, then I can save a copy. Okay, and then apply the same cluster file to a different project later on, and I can go in and I can just say export all the clusters. Okay, and so you can see that this new cluster file now is .egtp file. Okay, so I can export this and then import into a new project. So there's one thing I want to caution the user is that especially when we apply, when we establish or develop this .egtp file based on a very diverse germplasm, and if we want to apply this onto a project with segregation populations with our recombinant inbreds or double haploids, for those populations, in most cases we should expect only two genotypes, and so those clusters are based on the germplasm may not apply well for the populations, mapping populations. So maybe the good options would be to develop two cluster files, one designate for the germplasm and the other designate for the mapping population. So the last thing I want to point out is for the exporting the data. As mentioned before, that there is no option right now in the PC module for you to export data. But one possibility is we can go to the full data table. And so you can see that the samples has been assigned to each of the cluster. And so, okay, so let me go to the one like this. Okay. Okay, so we see some samples are assigned to the cluster, the second cluster, and some samples are assigned to the C1 cluster. And so we can export this whole data out, whole data table out, and then open up in an Excel file. And I also noticed that the way this cluster is numbered is you always start C1 from the left-hand side of the SNP graph and move towards the left. Okay, so in this case, if we have the SNPs that all giving me two clusters, then I can easily convert C1 cluster into the AA genotype and C2 cluster into the BB genotypes. If I have SNPs that giving me three cluster, I can easily convert a C1 cluster into AA genotype and then the C2 cluster into the BB genotypes, into AB genotypes, and the C3 cluster into the BB genotype. So this can be done, applied to the entire file. So if for some reason that we want to keep some of the SNPs that giving us more than three clusters, then if we want to convert those into the genotypes, then we have to do it one by one, individually, and we have to convert them very carefully. Okay, so that's just a quick demonstration on showing you how to convert all the clustering into the genotypes. So that's all I want to say about using the PC module for analyzing wheat data.
Thanks so much. That was well done. Great presentation. And any questions, we'd recommend that you contact tech support and reach out to us to get the user guide. And remember that anyone who has GenomeStudio's genotyping module and the installed key for the genotyping module is entitled to the Polyploid clustering module. So contact us and we will get that out to you. You can also download it through the GenomeStudio portal that's accessible through your your standard GenomeStudio genotyping module. So thank you very much for your time, and happy genotyping.